this presentation, we will talk about performance-based design, integration of building information modeling into the design process, and some of the applications beyond that. Structural engineering is the backbone of physical infrastructure development, including buildings, bridges, tunnels, dams, and transmission towers, and so on. And this physical infrastructure is the backbone of the economic development. So in a way, structural engineers are directly responsible for the economic development of the country and continuity of the life. They help to preserve the past, protect the present, and build the future through reduction of the risk to disasters to the built environment, so the economic development and life can continue. Disaster is a combination of natural or man-made phenomena, such as earthquake, wind, or fire, and vulnerability is the inappropriate or weaknesses in the built environment. And the exposure is the people and property that are affected by this hazard. This risk can be reduced if we can reduce the vulnerability or make our structures perform well when subjected to particular hazards. To do that, the structural engineering has to develop its methodologies, its design process, and its approaches, and also integrate the emerging technologies into its process, such as AI, robotics, and so on, and also develop the use of appropriate tools, software, guidelines, and other methodologies that can help the process. Over the years, the design approaches have been developing, especially for seismic design, starting with intuitive design to code-based design, where several factors and various procedures are specified to tackle certain types of structures and hazards, to performance-based design, where the performance is explicitly evaluated and compared against the hazards. That leads to consequence and risk-based design and to resilience-based design. And finally, the application of other technologies that assist in the design solution and also in the control of the structural response. Earthquake has been first to adopt many of these approaches, and wind design is following in its footsteps. Currently, mostly it is done by code-based design, but many countries it is also progressing to performance-based design. So let's look at the performance-based design first. In performance-based design, hazard and the response fight directly and fairly to determine vulnerability, taking the code-based factors and restrictions out of the equation. So in this case, the appropriate hazard and the vulnerability are compared directly to see whether the structure will perform well or not. The basic concept behind performance-based design, therefore, is to take the structural response, which is determined from the basic material response, such as steel and concrete, and the cross-section dimensions and the configuration, to determine the cross-section response, which in turn leads to the member response. And finally, to determine its capacity through a pushover curve or any kind of nonlinear determination of the response. On the other hand, the earthquake risk or seismic risk is determined through the time history of the ground motion, expected ground motion, converted into spectral acceleration and to spectral displacement, so that the two can be compared directly. This comparison between the structure's response and the hazard or the demand leads us to a common point where we can determine whether this performance is acceptable or not. And if this common point does not exist or is at a location which is not acceptable, then we can go back and modify the design, increase reinforcement, modify the materials, and so on, until we get the response that we expect. Therefore, the design decisions are explicitly linked to hazard levels and the key performance indicators. The key performance indicators in structures can be many, but here we can consider some of them as the most important one, especially for the case of buildings. The first one, of course, being the stability, that the structure should remain stable. Second one is the strength, that the parts of the structure which are strength controlled should not fail. And then the deformation, the structure should not deform a lot. Drift control between the stories, ductility of the members that will provide sufficient resistance to seismic demand, and energy dissipation together with ductility that will dissipate the seismic energy without causing unacceptable damage. And finally, the motion perception, that means acceleration and velocities and displacements produced during the dynamic response. To carry out this kind of a analysis and to determine these indicators, we need a thorough understanding of the nonlinear dynamic analysis. We also have to have an agreement of various stakeholders which are involved and to obtain the right information about the site and the materials. And we need to have the right kind of software that out this analysis and the guidelines to follow. Most importantly, we need to have an ability to interpret the results in performance terms so that we can see whether a certain response is acceptable or not. And because this is a very intense and complex process, we also need a lot of patience because it might take much longer than the traditional design. The stakeholders involved in the performance-based design include, of course, the client and the architect and the structural engineers. But on top of that, we also may need a special PBD specialist or a PBD consultant, a PBD design reviewer, and a site-specific consultant, all working together to ensure that the structure has the expected performance as required by the client as well as by the typical structure that we are designing. Some of the guidelines being used in US and other countries are derived or based on these basic documents, most importantly coming from PEER, NIST, and other organizations, including ASCE. And for tall buildings especially, the TBI guidelines are considered to be the standard that most people follow while conducting performance-based evaluation. There are several tools available to carry out the analysis, but from CSI, the three most commonly used tools include ETABS, which is for building analysis and design and has full capability to conduct nonlinear analysis and performance evaluation, and Perform 3D, which was specifically developed for performance evaluation, and SAP 2000, which can be used for the nonlinear dynamic evaluation of any kind of structure. The first step in this process would be to determine the right kind of hazard levels. And typically for seismic evaluation, two levels are used. One is the service level, which corresponds to a 43-year return period earthquake, which is expected to occur frequently. And the second one, which is the MCE level, which is a rare to very rare earthquake event that may come only once in 2,500 years, roughly. Once the appropriate hazard levels have been defined, the next step is to define the corresponding acceptance criteria or acceptance levels. For example, for a service level earthquake, the frequent event, the structure is expected to remain fully operational. Whereas for a MCE level or rare earthquake, the structure might be expected to damage heavily or lightly, but in any case, preventing a complete collapse and loss of human life. To start the process of the analysis, the first one is to always determine the modal response and look at the natural period and the mode shapes as well as mass participation ratio to make sure that the model has been created properly and that the model has the right basic dynamic response and the natural periods are within acceptable limits, as well as the mass participation ratio is appropriate for the structure to move to the next stages of analysis. Once the modal analysis have been determined properly, then we can be assured in a way that the dynamic response, which is a summation of individual modal response, will be adequately computed. The next step would be preferably to look at the nonlinearity of the structure and capture the nonlinear response before carrying out a full nonlinear dynamic analysis. This is typically done by carrying out a pushover analysis, which is a nonlinear static approach using monotonic loading. And this basically gives us some indication of the structure's nonlinear capacity, as well as its relationship with the yielding of various components, its weaknesses and its strengths. In this particular video, we can see that the structure is deforming, and while it is deforming, it's also yielding, and the damage is occurring in some of the components at various locations. And this kind of analysis is useful to make sure that the nonlinear properties have been defined adequately. The next one would be to carry out a full nonlinear time history analysis to determine the structure's vulnerability to the particular earthquake. In this case, several time history have to be defined or determined, and the analysis has to be carried out typically from 11 up to 20 or even 30 trimetry analysis, depending upon the type of earthquakes that we are considering, as well as the type of structure being analyzed. In this animation, we can see that once the ground motion input is provided to this nonlinear model, we can determine where the damage will start as the earthquake progresses, and then we can monitor this response of various components. In this case, we can see that some of the connections and joints are first reaching their capacity, then followed by various other members in the structure. And we need to continue this analysis until the entire ground motion is complete or the structure fails to continue to perform well. Once the nonlinear analysis as well as linear analysis have been completed, it is always a good idea to compare the base shear generated from various types of analysis for various types of demands, so that we can get a picture of the level of forces being generated from earthquake, from wind, at MC level, and at the service level. This also provides a sanity check on the structure's overall response, because these percentages should be within a reasonable limit. Another important evaluation that we can do, especially for tall building, is the modal separation analysis, where we can look at the demand from in each individual mode. And this helps us to see what are the effects of the higher modes contribution to the overall forces, as well as the shear at the base and the moment at the base. In this particular slide, we can see that the moment distribution along the height varies significantly depending upon which mode is being evaluated. And in some cases, the yielding of the structure may be only occurring in the first mode and not in the higher modes. This is especially true for shear, where the contribution from higher modes to the overall shear is much more significant than for the moment. This kind of analysis, which is done on top of the basic analysis, is always helpful to get more clear understanding of the yielding as well as the reduction of the demand from various modal contributions. We can also look at the shear capacity of the shear walls, which is a brittle kind of a failure, and that gives us a control on the strength capacity of the shear walls. And this satisfies one of the 2 KPIs, one of the 7 KPIs, which is the strength. Similar checks can be done for columns and other components which are force-based. We can also compare the lateral displacement for various ground motions along the height, which gives us checks on the deformation and stability of the structure. The axial strains in the shear walls can be evaluated both for tension and compression, which gives us a control on the deformation and yielding. The transient and residual drift checks can be performed for the structure for each ground motion, also for the average, which gives us a control on the drift. It is important to note that the residual drift should be determined once the structure has come to a complete stop after the ground motion has been analyzed, to see if there is any residual drift in the floors to ensure that the structure is not damaged during the event. We also need to check the coupling beam rotations, which are acting as typically the building fuses and contain a lot of ductility as well as energy dissipation, and to make sure that they do not collapse. And this gives us a check on ductility. Another important check is the dissipation and balance within the structure. So energy balance in terms of the total energy from various types of energy, for example, elastic, damping, and so on, and the inelastic energy coming from the deformation and the ductility can then be further investigated into various components such as shear wall, coupling beams, and diagonal reinforced complete beams, and so on. This gives us an idea of which components are providing the most ductility and contributing to the energy dissipation, and they should be designed and detailed more carefully. This gives us a control or check on the energy dissipation levels. And the last one could be looking at the absolute acceleration of each floor. And this is useful information because we need to control the motion perception by the people occupying the building. This analysis that we have just talked about is typically for earthquake, and it is commonly used in many countries to do the performance-based evaluation for seismic design. Similar approaches or similar guidelines are being developed also for wind design. The most recent document being the pre-standard for performance-based wind design by ASC, which also provides guidelines on how to do nonlinear evaluation of the buildings for high or longer return period winds, and also for more controlled perception at the service level. The wind PBD is an area that is being developed, and it normally needs to be carried out together with the wind tunnel study. We have looked at the performance-based design. Let's also look at the resilience-based design, which goes a step beyond the basic evaluation of the structural performance. This looks at not only damage to the structure, but also its effect on the loss of quality of life, the economic losses, and the loss of community and culture. This looks at resilience as a bigger impact rather than purely the performance or damage to a particular structure. So in addition to the damage or loss of the structure, casualties, downtime for rehabilitation or retrofit or repair is also looked at. And also the cost of such repair is evaluated. This complete evaluation of the impact of earthquake leads us to provide more information to the community in terms of the resilience of the entire system in which the structure is one part. And this can help to determine the sustainability as well as resilience of the community. Just like the US Green Building Council was established a long time ago to look at the development of green buildings, a similar organization has been established, which is US Resiliency Council, which looks at the resilient buildings. This initially started by many organizations, mostly led by Arab and supported by the US Resiliency Council, and came up with the standard called READY, or the Resilience-Based Earthquake Design Initiative. This has been developing in continuation of the earthquake seismic design and the performance-based design. Let's look at some of the key components of the resilience-based design. And the first and the most important one will be the importance of non-structural components and the damage caused to them during earthquakes. It has been determined through studies that the structural cost is not the primary cost in a particular building, and the cost of the non-structural components and the contents is much larger than the cost of the structure itself. So while the structural performance is important, protecting the non-structural component and its content is even more important in terms of the impact on cost and rehab time. So the overall process used to carry out resilience-based evaluation, including the performance-based evaluation, will include all of the steps involved in the PBD. And after that, based on PBD, we can then determine indicators such as the explorations, flow displacements, flow velocities, and then use that information to determine non-structural damage. And from that, we can determine the direct economic loss or the repair cost, also the downtime, and also any possible serious injuries or casualties, and the business interruption cost. All of these together, when evaluated, give us an idea of the resiliency of the particular structure. This kind of evaluation is far more useful to the community than purely designing a structure to code-based procedures. Let us look at building information modeling and its relationship to structural design and detailing. BIM has become a basis for managing the entire project lifecycle information, and many stakeholders, including the architects, engineers, contractors, material suppliers, are now using BIM as the platform for conducting their work. BIM can be an integrator of information because it provides us with a way to correlate the various information of the project with a particular member or particular component of the structure, which is parametrically defined. And this relationship and this physical nature of the information gives us a way to manipulate and manage the information in a more consistent manner. BIM has been expanding its dimensions in terms of how many life cycle components it handles. In the beginning, it was restricted to 3 to 4D, means dimensions and time, and then until 7D, which includes management, sustainability, and estimating. And now we are also seeing expansion to safety, linear construction, and industrialized construction. Similarly, the level of detail represented in BIM models is also increasing, and from LOD 100, which is a basic information, all the way up to LOD 700, which contains the information not only of the structure to the final detail, but also information on how to dismantle or decommission the structure. So we can see that both the dimensions and the level of detail are increasing. Structural engineers can take advantage of this enhancements in the BIM model. ETABS, for example, carries out the design and detailing of reinforcement in a very integrated manner. And this automatic detailing is then available for users to edit, and they can edit this detailing, and after that they can produce 2D drawings, BOQs, Rebars, and 3D cage. However, to make it compatible with BIM models, this information is also transferred to other software. First in 2D drawings, for example, through CrossCAD to AutoCAD, and through a complete information model through IFC, and which other software can then connect and utilize, and more directly through Cross-Revit to Revit using the full BIM implementation. This fully integrated detailing, not only within the program, but also with other programs, provides a great opportunity for structural engineers to share and use their information across various lifecycle steps. This is one of the views in showing various functionality available in the ETABS detailing, which can detail concrete beams, columns, slabs, and walls, in addition to steel columns and steel beams. The detailed reinforcement is converted into a 3D model, as you can see here, with every rebar individually shown. This information can also be used to update the design capacity and also to prepare drawings and various cross-sectional and elevation views. As you can see from here, that this information can be edited by the user to refine the design, customize the design, or to provide reinforcement as needed at various locations. They can also use the views generated by the program to create the drawings as they deem fit. These drawings can be printed directly or can be exported to other formats. This editing ensures that engineers have full control of the final detailing being produced. This information, once completed in ETABS, can then be transferred through IFC, and which can be opened by other programs that work on IFC models, and also through Cross-Revit to Revit program. And Revit program, this information can be edited, can be modified, and also brought back into ETABS. And as you can see here, the reinforcement gauge is represented by proper families within the Revit environment. In the future, the reinforcement generated by directly working with BIM models could be used as a basis both for preliminary design, for detailed design verification, cost estimation, BOQ generation, bar placement, schedulers, clash detection, and so many other purposes. And this can be expanded to other components. And this is the way CSI is working towards integrating reinforcement detailing into BIM models. Let us also look at some of the other applications of related technologies in structural engineering application. The first one is the use of imaging through drones, through cameras, and also through LiDAR scans to create 3D models. And these 3D solid models can then be used to create the appropriate structural models, and the response can be determined for a given, such as earthquake or wind. And this can help to preserve the historical buildings and existing structures for which direct measurement may be difficult. Similarly, scanning, both LiDAR scanning as well as drone imaging and other imaging, can be used to create models of the existing structures, and then 3D printing can be used to print such models, and they can be then placed in the wind tunnel to determine their response to various levels of wind. And this information can be brought back into structural models to determine the response for the time-varying wind pressures. For example, here, the results from the wind tunnel analysis are used to carry out a linear time history analysis for wind for this particular structure, which response is quite important due to its flexibility. We can also use the cloud-based systems to provide access to engineers for the structural information using their handheld devices on the go. This is quite useful because many times this information can be helpful on making decisions at the site. AI models can be used to predict the response of the buildings when they are appropriately trained on existing structures which have been previously analyzed and designed, so that for the preliminary design, we could use the architectural design input and directly obtain the code-based design or performance-based design indicators. And this can eliminate the time needed to carry out this complex analysis, especially for the preliminary estimation, and also providing a sanity check on the results that we have obtained by comparing it to the previous experience. So in this talk, we have covered several topics, including performance-based design, consequence-based and resilience design, as well as the assistance of various technologies in structural design process. We hope this information will be useful for you in your structural design as well as in the future work. Thank you.